Second speaker is Suen Hou. The title is Search for Neutron Resonances in Vector Boson Fusion Atlas. Please start.
Thank you for the opportunity to have this chance to show the Atlas data analysis. And I follow up a little bit on the Higgs. The next object is the reverse the boson, vector boson fusion in the search. So this will be the first slide to show you on the Atlas. So we are all aware with this accelerator and the experiment. For example, it's a PP collision that is provided. So in this kind of collision, the analysis I'm going to present to you is about the parton collisions from QQ. And the experiment we're talking about for the data analysis and the details about it is that if you look at the person is this size, so this is a very large experiment. It's about 6 floors high. So on the Higgs issue is that before the Higgs was discovered, there's some doubt to see a possible alternative to understand what the mechanics could be. For example, at the time, vector boson fusion was quite hard to discuss. If the Higgs is not there, what are we going to do about it? For example, this diagram, if we are only going to have a vector boson fusion to give you a W pair, like over here, this is diverging cross-section. So the cross-section will look like this. So when the center mass energy is enough, you see cross-section rising with center mass energy. Right? That'll be really exciting if this is happening. Right? So the future will bright up as you see a lot of event production will be in the future. So after the Higgs discovery, this diagram must come in. And the fact is that this term is going to cancel this diverging behavior. So in total, in sum, the unitarity will be conserved and everything will just fall down. So the C is at deep and it's dark. It has been. So that's about the analysis initiated before the 13 TV. When people look at this, are really excited about the possible potential in understanding some picture over here. So are we really over with this vector boson fusion in the search? Is that if everything is just a standard model, of course, then it'll be just a point light as is shown over here. This diagram is dominant. This dotted backline here is not so clear. It's from this paper. So a lot of the review in this paper, and also the Monte Carlo coding out of this paper. Author of this paper, and the Higgs out of this diagram, right? So if these two are dominant, very much everything is just standard model, then we do not really have to look much more. However, if it's not, for example, it's partially, then it becomes a block of something. This something is for us to find out whether there's something there or not. This kind of diagram is not too exciting, too surprising. For example, 2 photons like this. 2 photons physics at the E plus E minus is exchanging photons. And they have a block of a very rich interactions, giving you resonance, giving you power point like jets and so on. So if this block is there, then possibly there'll be a new resonance. Whether it's a resonance or not, it's really not so obvious or clear for us to define it. But it doesn't matter. Let's just assume it's a resonance. For us, for the data analysis, that it makes it easier to define the final state. And as I said earlier, in this paper, the authors is coding a software called Wizard. And inside there, they provided a lot of model possibility for experiment to make comparison or to make search based on the distribution predicted. So upon the Monte Carlo being provided, we are going to observe this kind of behavior. The show me there is not so exciting to see it, but it's already low in cross-section. So at 7 we do not really get too excited about doing that because cross-section is just just covered by the QCD jet, for example, and it wouldn't be significant to look for anything. But at the 13G, we start to have the opportunity to have a sizable cross-section. And the final state is that the two colliding quarks will give you two partons, will give you two jets. And in that blob, it'll give you, say, a W pair that'll be observed as a lepton plus neutrino, and the other W is the same thing. So that's the most clean final state to look for, just two lepton with missing PT by the neutrino, and plus two rather energetic jets. So by tagging the jets, we know something like this is happening, and their opening angle must be really large. So the analysis actually in collaboration with the USTC and with some young fellow we are supervising with professor there. So this has been carried out for many students and many generations. For example, we look for the two charged leptons, missing ET and jets. So before this conference, actually I gave a talk on SUSY. So in terms of data analysis, why this is so different from the previous one I presented on SUSY? We also did some neutral mesons, neutral resonance in SUSY search, right? It's in general, everything to us, data analysis, we are very much looking at the similar final states. And it is for example, this time we add in a jet in forward direction. So it's all based upon the Monte Carlo prediction and our comparison with the Monte Carlo. And in the end, it's actually just standard model analysis. So before that, I say that this is initial analysis that we started with 2015, and in that year is the total amount of data is not that large, so it's only 3.2 femtofarad. In this analysis, all the modeling is based upon the wizard. For example, this modeling provides the benchmark, for example, the scatter resonance, the vector resonance, and the both tensor resonances. Each one is independent, is analyzed independently, for example. So there are at least 5 possibilities, and their prediction on angular distribution and final states to compare with. This is in terms of the modeling. Is that if there is a new resonance plus the standard model classical electron weak interaction to produce the W pair plus two quarks final states, and the interference of them, minus the continuum background, or called background now. And then that's the excess of signal. For example, if its resonance is so obvious, there will be spikes. It's assuming a one type of meson, F, and at different energy with 200 GeV and so on, getting higher, and then the spike is clear. This kind of signature against the standard model background makes it easier to search. And these are cross section, and that is falling with the resonant energy, for example. Now in data analysis, everything really is going against the standard model background. So what kind of background we have? The project, that's just first order standard model final state. And the taper is getting so large in total cross section, and their final state is so energetic. So these are the dominant ones. The others are, for example, gamma jet, Z gamma plus jet, for example, diboson. And so diboson is what everything starts with. For example, Higgs search actually going against the ZZ of the diboson. And Higgs search is in the same diagram as the diboson induction. And another rather large background is W plus jet. This is because the cross section QCD, the cross section is like 1,000 times higher than whatever you want to look for. Monte Carlo background is there are plenty of packing to be chosen from. For example, over here the ETD and Z plus jet and so on. These are all being kind of forced into a much higher order. For example, NNLO calculation, in particular for the PDF of the colliding partons. And the Monte Carlo by itself is absolutely not to be trusted. So there are some correction or calibration and to be compared with data, for example, the PDF density, the jet distribution, and so on. Now let's look at the background. or in terms of VBS resonance search, or in terms of SUNY, so whichever, everything is going against the background. Background, the real thing, is what the detector is observing. In our case, in this search that we demand for 2 lepton final state plus jet. So Z plus jet is dominant, for example. TT bar, the top physics. Z plus Z has 2 same flavor lepton final state. So it is in the search for E mu mu final state is there. However, if you want to look at E mu, that the background, the situation become much cleaner. And if the signal is there, then what you're going against is the top pair production. So the distribution like this. There's a mu mu, E mu mu, and E mu final state top is dominant. And in the analysis, apart from the search for signal, the background or the standard model must be validated to make sure that our data understanding is correct. So for example, by characterizing the Z plus jet, this is asking the Z-like of the lepton pair to be really close to the Z, and we make event selection and make comparison, right? So the events are really just following the green is the Z-jet dominant. The distribution really go agree with data, and we have more plot to show that this is suggesting the event dominant of top pair production. This is the yellow color distributed here, and this is by selecting by B-tagging. B-tagging is very useful. Top will go to B, but W won't. So this is one dominant feature to distinguish W from whatever the ground. So the agreement is shown up here. This is shown on the transverse mass. As we said, it's a final state looking for two lepton or 2 W that decay into lepton neutrino. So the 2 lepton transverse mass is one of the key characteristics as formulated up here. Is by the leptons observed calculated mass. And the final and signal region that we consider where the signal should show up is in the distribution over here. Over here, we do not have the molecular prediction of the signal, how it will look like. These are all just background selected. Out of 3 points, of the 3 points, it was spent up par of 2015 in 1 year. The channel has collected a couple, several dozen events under 100 in total. And then we have these distribution. In principle, is that everything is still fall in agreement with the center mode background. And there's no excess. Sorry. However, there's a something to say is that for those 2 lepton, scatter particle prediction, we do have a crossing of observables with a static higher than the prediction. But there's crossing. We know that below this, the red and the green crossing below it, it's not likely to have any possible signature for the 2 resonance being predicted. However, above it is still in the search. And with the increasing amount of data, the cross-section, the observable will be higher, and we can reduce the prediction lower and be able to predict the range. For the vector and tensor, the observable, the amount of events are similar to field. So the statistic is not enough to define a fine distribution and upper limit of 95% confidence level is still much higher than the expected theory, the red theory. So we just know it's below that, and we cannot define it. The first year was planned and practiced by our group, and it was published as a confidence note. And after the year 2006, the accelerated data improved very much, and the total amount of data is collected 10 times higher. And this topic is picked up as one of the Atlas Higgs group analysis. The effort is expanded. Instead of just using the wizard suggested model, now we have the model actually many more models are introduced for comparison. And the mass range can, with the statistic about 10 times higher, the mass range increased from 500 to 3,000 GeV or 3 TeV. However, in the analysis strategy, everything got changed a little bit. For example, in the collaboration analysis, the E mu got dropped to keep only the E mu. We know that E mu can only be W pair, cannot be Z. So the final state to look for is much cleaner. So the contamination from Z in the same model is much reduced. And the catalog is it's not here yet. Right. And the jet tagging is also required. Let me come to the selection and spread that. So the model are complete changed. For example, we are using the narrow width of heavy hits and a large width of heavy hits. These are scattered. And this is a GM model to provide another scatter resonance to look for. And then there's also the vector and the tensor of different models. For example, this triplet model and this Lagrangian model that suggested spin 1, spin 2 particles. So in total, we have 5, and these 5 are different, completely different from previous one. And in selection, the tagging, as we said, the W pair are now look for E mu only. And the tagging condition is that we ask either 1 or 2, or more than 2, for example. And then criteria differs on the number of jet. It's a kind of in all the similar selection, in final we divide it into 1 jet or 2 jet. So it's also good to have 2 data types in terms of a comparison of the prediction and so on. It's also good to have two categories. And the discrepancy are still the most powerful is the transverse mass in this analysis since the very beginning. For validation of this correctness in data analysis and the predictions, there is a control channel. For example, in highlighting the W pair of the standard model of the top physics section. The top again is based on B tagging. Top go to B, but W won't. So W pair is asking the B tag equals 0 and selecting other parameter, for example, the mass that time. So in such a way, we have 1, 2, 3, 4 categories in data analysis. And the result in comparison with the Monte Carlo will make it a better solid on the prediction. And the background, for example, this W is going to E mu. So we still have this top of physics, W physics, and other small fraction of them. And for the one final state jet that tag the other mass in the midnight, we have the top background and the W pair background. And if we ask for 2 jets, and it is in principle just top background. And these 2 categories are analyzed independently. And eventually, there's a still question is that whether Monte Carlo prediction with the W pair or top are correct or not. There's a scaling factors. But between them, it's based on PDF or based on other parameters. We probably can make things wrong, and there's a fitting for those 2 categories, and they may make the final state background fractions more reasonable. And that's about the Monte Carlo preparation for the data analysis. So in the control region, for example, in the top highlighted control region, that's asking 1 jet. This time, the statistic increased by a factor of 10. So you see the distribution is still beautiful, all is a distribution. And if we ask for the W pair, the distribution also very, very nice. So it's one thing, the number of events that got selected are agree, and also the shape. The shape are also in very good agreement. This kind of analysis, in addition to many other analysis like SUSI, are all been building up the confidences that we understand among the standard model really well in this experiment. So access, whether you are looking for resonance, for high PT, for whichever, it must be trusted because all the background got beaten up so much that if you can make agreement on the background and any exit out of background in any distribution means something real. So look at this statistic here. we have the 4 categories and amount event now amounted to like 1,000 for the signal. Right? And this is a dominant background. This is taken statistic up to like 6,000. A distribution over 1,000 already means the distribution, and agreement means a very good systematic treatment of the detector and the analysis and so on. So if we look at the transverse mass, that distribution also agree very well. This is logarithm. So if you now we just blow it up, and this is the difference in ratio. Other than this being at the height, everything is really quite good. On statistics, it's just some table showing all possible being evaluated for the top background from different categories. These are in percentage. So the systematic is not being estimated up to like 20%. It's quite high actually. So within the 20% systematic, everything is within the standard model prediction. That's how the picture we have so far for this. So for seeing nothing in excess is that for the scatter boson, scatter resonance, this channel, the narrow heavy hits and the large with heavy hits. The first point, the latter point, can more or less be decided on how large the percentage could be. And for the vector and tensor, as previously, the theory is still much under the data observables. So we still have not clear yet, not near yet to really have a chance to make a detection or make an exclusion of these particles. So in conclusion, this is based upon 32 inverse van der Waals analysis of 13 TeV. That's all the data set so far now. In search for the vector boson fusion into heavy neutral resonances. So far the cross-section as it has been analyzed, it's not showing any obvious possibility of having excess. And of course the data, amount of data is still rather limited. We are not close yet to really observe any vector boson fusion resonances. Thank you.
Thank you very much. So, question time.
Are their backgrounds come from tau lepton pair production?
Of course they are. So that's a good reason. Yes, of course. Now I didn't talk about tau at all because tau to lepton is about 10 or 30%. The fraction not that large, but there. These for this channel, we are looking at immune. There's a Zeppler jet, a very small fraction here. This will stay there because the Z go into tau into electron and muon.
I mean, there are also taus which don't come from that, but yeah. So there are.
This is the dominant one. W of course also go to tau.
Okay.
Any other question?
Yeah. If you also open the electron pair and muon pair channel, will you be doing better?
It's a cleanness.
You
Of
know,
course,
you have-
we can do it.
Yeah, I know you can do it, but will you be better?
In terms of expressing the result, no.
No, okay.
Because if you look at the say the final plots here,
Yeah, the final.
this is the immune final state.
Okay.
If you add an electron channel, it's the thing more or less comparable from the previous analysis.
Yeah,
But
from the background about the same.
yeah,
Yeah, okay, but you have 3 times more statistics.
that's true. You can do combine, yes, that's true.
But you don't expect it to be better.
Well, in this official analysis, it's not included.
Okay. But
In terms of analysis, of course, we can do it. Actually, we practice.
Okay.
And then depending on the pressure and dissolve property, it will just stop somewhere.
Other questions? Or comments?
Thank you.
If not, let's thank Suen again. third speaker is Suen Hou. The title is On the Shoulder